Hey, good morning, everyone. I want to welcome you to another multivariate statistics class. Of course, we started this material yesterday. Inferences about multiple mean vectors. Um, I remember in the outline for multiple mean vectors, um, we have a paired comparison, repeated measures, or two populations, one way ANOVA, simultaneous confidence interval, equal covariance matrix test, and two-way multivariate analysis of variance. But I think I for first walk you through the univariate version of two sample t-tests. I remember I walk you through dependent samples. Then I show you the multivariate extension of that, okay, and how to handle the repeated measure aspect, the contrast matrices, the Ortelinti squared, and so on like that. So, I also show you some arrow code. So how we advise from time to time, you get yourself familiar with the arrow codes. So, where we want to start today is from the independence. I walked you through the dependence test yesterday, and I'm also going to kickstart from the univariate because the moment you understand the univariate, you'll be able to generalize and extend to multivariate situations because um, if you really want to understand the multivariate technique, okay, so you need to first get yourself familiar with univariate technique because what we're going to do is just the extension of the univariate technique. Now, if I want to conduct an independent test, I have two population. Maybe I'm only focusing on one variable. Maybe I'm trying to look at the standard of living, comparing the standard of living in two countries. The H naught is going to say the difference between the standard of living in two countries is mu naught against it is naught. And of course, situation, we have assumptions that we use, when we have two populations, we want to compare means for independent tests. The assumptions, apart from normality, assumption is as do we have the same population variance? If the population variance are the same, we're actually going to use the idea of a pooled variance. Has anybody heard about pooled variance before? Pooled variance? We normally pool our variance when it is assumed that the population variances are the same. So because of that, if you take a look at this guy now, so this is pooling the variance. The x1 squared is a sample variance, from the first sample. The S2 squared is the sample variance based on the second sample. Of course, the N1 and N2 is the number of sample taken from each group. Okay, so uh, if you take a look at this formula now, this is a test statistic. In the two group, I'm only focusing on one variable. I could be focusing on maybe the means the score, the difference between the score in maths between two schools. Okay, just one variable. Okay, mathematics performance, performance in maths. Okay, so this is focusing on one variable. And I told you, statistical inference is in two versions. Statistical inference is about, number one, testing hypothesis. As you can see here, you can see I'm testing hypothesis here, and of course, I'm going to have a test statistic for doing that. And also has to do with the constructing confidence interval. So there are two. We talk about confidence, we talk about statistical inference. Do we want to test hypothesis about the difference of means, or do we actually want to construct confidence interval? Okay, the confidence interval that will contain the difference of means. Okay, so that's why you're seeing this guy here. Okay, and you know the XP here, okay, is going to be the square root of the pool variance. The study that is very, very crucial. If you, whether you want to test hypothesis, you can see SP, right? Or you want to construct a confidence interval, you can see SP as well. So the standard deviation, the standard deviation of the pool estimate is very, very crucial in statistical inference. Now, now that you understand the univariate fraction of two sample t-tests, independent tests, then we can now, what of a situation where we no longer want to focus on one variable, probably between two schools. I want to compare the performance in math between two schools, performance in reading, and performance in science. With that, I'm actually going to go multivariate. So we're going to call that multivariate independent samples t-square test. So we're going to have a situation whereby you can see SKI identically and independently normally distributed with a mean and covariance. Now, K here means I'm only focusing on two groups. But when I'm focusing on two groups in group one, the numbers of variables of interest is going to be more than one. And in group two, the numbers of variables of interest is also going to be more than one. That's what we mean. Now, we also want to have, and we want to have a situation whereby the two groups, even though they may have different means, but assumption is that they have the same covariance structure. And having the same covariance structure, we mean that we actually going to make use of a pooled, variance. Now, I needed to pay attention right here. This guy here is a pooled covariance. In the case of it, when we're considering the univariate case, we have a pool variance, right? I'm going to show you. I'm going to go back. You're going to see that, okay? In a univariate case, so I want to see, I want you to have the opportunity to compare the univariate with the bivariate, with the multivariate. Take a look at that. That's for univariate. Okay, that's for univariate. But for multivariate, we actually each of these we actually be a covariance matrix, a sample covariance matrix. So I'm going to have a sample covariance matrix from the first group. I'm going to have the sample covariance matrix from the second group. Okay, and I'm actually going to have a full sample covariance. So which is what I'm actually having here. And the question about this. So this guy now, that's a pool sample covariance. This guy here, sample covariance for group one. This guy here, sample covariance for group two. Don't forget, each group has more than one variable. The fact that they have more than one variable, we can actually construct sample covariance based on that. No, this is the formula. Now, if I now want to, how will my hypothesis going to be in this case? My hypothesis is going to be in that form. The mu1, the mu2, they're going to be vector. Okay, and of course the t-square, the formula now, okay, the formula that I'm actually going to use in that regard is actually this. Can you see that? You can see your SP, the pool. This very XP here is the one you derive from here. Okay, and you can see you find the inverse of all of that. So that will give you the Otterlin t-square that will serve as the test statistic for the test. Now, after that, the next thing we want to talk about is, can we also, under what condition are we going to reject the non-hypothesis Then we're actually going to compare the test statistic, okay, this guy. We're going to compare that with this guy. Okay, give me 1 second. We're actually going to compare. This is going to be a critical score. This is going to be the test statistic. So when the test statistic is greater than the critical score, the null hypothesis will be rejected. Okay, so is there any question on that? Is there any question on that? Okay, if there's no question, there are two ways to take decision when you are conducting hypothesis testing. It's either you compare the test statistic with the critical value. When the test statistics is greater than the critical value, you're going to reject it, should not. But what if in a situation where you want to make use of a p-value? Of course, we always compare p-value with the level of significance. Okay, when the p-value is less than the level of significance, we're actually going to reject the null hypothesis. So the p-value is going to be the probability of a t-square, like what's called that. Now, at the same time, you can also figure out the confidence interval. So if I consider the probability of a t-square less or equal to that equal to 1 minus alpha, what do we mean by 1 minus alpha? 1 minus alpha means confidence level. If alpha represents the level of statistical significance, then 1 minus alpha will be the confidence level. Just wanted to take note of that. Okay, now how do you do that in R? I provided the multivariate independent sample t-square test. So I will advise that you study all of that. Okay, now based on the example, we have a particular data in R, it's our IR inbuilt. Okay, we actually have data set on, we call that empty cows. And one of the variable in the data set is actually cylinder, and the cylinder is categorical. Probably the numbers of cylinder in an engine. Okay, here, and let me tell you this, pay attention. Okay, I needed to pay attention. Now, if you take a look at cylinder, X4 represents, we want to consider cylinder 4 and some of these variables. Cylinder 6 and the same set of variables. Cylinder 8, the same set of variables. I want you to pay attention to that. For instance, if I actually want to compare X4 and X6, don't forget, we are dealing with two groups at a time. Two groups at a time. What make it to be two groups? What make it to be two group is cylinder. Oh, this group has cylinder 4, and this group has cylinder 6. But each of these group has the same numbers of variable. They have the MPG, they have the DISP, they have the HP, they have the WT. So what I want to compare now, okay, I really want to see whether MPG is going to be the same in these two groups. DISP is going to be the same. Okay, I'm trying to look at whether there's a significant difference between MPG in two different groups, DISP in two different groups, HP in two different groups, W2 in two different groups. And what is the agent of classification here is the number of cylinder. Do you know I can conduct independent sample t-square text here? Okay, and you know what? Oh my God, the moment you have your data in, you're just gonna do t dot test of that. Then you're just gonna be focusing on the p-value that came out of the test. And of course here, asymptotic false. What asymptotic false means is we don't have a large sample. Asymptotic true with me. So here it means we have a finite sample. So what does the p-value talk about? Do you know that arrow have saved us a lot of time? You know what we're supposed to do here. If we want to compute this manually with a data set, we are expected to do all of, I'm going to show you. Oh my God. You are expected to do all of this. You get your t squared, you get the p-value associated with t squared. But you know what? With a simple coding now, okay, with a simple coding now, I got my p-value. Okay, now get my p-value now, get my p-value now. 0.0017 is less than any reasonable level of significance, then we actually go to reject the null hypothesis. You do the same. I can compare S4 and S8, X6 and X8. I'm actually comparing two at a time. Don't forget, we're dealing with two groups. Is there any question here? Any question? Okay, you are good, right? I'm actually going to move. Now, if you take a look at what I did the other time, okay, when I was comparing the two groups, under the asymptotics for each comparison, I indicated false. That indicated false. You know, if you do this, t dot test into the two variables is into the two groups, automatically you are telling the R you are working with a finite sample. And that's why arrow is automatically going to indicate false or for asymptotics. But what of situation? How do we modify the test if we have asymptotics like samples? Okay, you know what you're actually going to do. You know, for instance, I want to compare finite with the large. Pay attention. Take a look at this. Can you see it? I mark false, true. There I'm comparing the last sample with a finite sample. So take a look at that. And you know, I'm simulating data set here. You know what I'm actually using 42 groups. Okay, we can simulate data set. Okay, we can simulate. I simulate data set. Sample size n equal to 10. Okay, and 4 indicates I actually want to have 4 variables, and I'm simulating that from normal to artificially simulate data from normal in R. It's going to be our norm. Okay, so we can compare between the finites and the asymptotic. That is what this page is talking about. That's what the page is talking about. Now, I told you statistical inference that we conduct come in two versions. One, hypothesis testing. The second one, the confidence interval. Now, this is the simultaneous confidence interval. You know, some of you may be wondering, why are we interested in confidence interval? Example that I cited where I actually want to compare performance of students in two schools in three subjects. What is the significance of simultaneous confidence interval for independent sample t squared? I actually want to see, I know the difference exists between the performance in mass in this school and in this school. If I have a single number for the difference between them, that's a point estimate. A point estimate could be wrong or right, could be low or high. Because of that, we actually want to construct a confidence interval so that we can say the true difference between mathematics performance in this school and this school lies between interval, lower bound, upper bound. So we're going to simultaneously have that for all subjects. This is the formula that we're actually going to use for that. So what if in exam, I'm actually going to ask you to compute that? This is the formula that you're going to use. Okay, now don't forget in the XP, in this formula, the SP is a pooled standard deviation. Okay, the SP, oh sorry, the pool covariance matrix, SP, the pooled covariance matrix. Okay, now now this is another version of that. How do we do that now? There's a code here, which I advise you to study. I also want to use the code for the real data. The other time, we try to find a difference between two groups, and we look at the difference across four variables. We also want to do the same. Now, uh, we are actually talking about two groups here. Take a look at that. The group is actually distinguished by the numbers of cylinder. It's like I have cars. I categorize cars into two, those with four-cylinder engine and those with six-cylinder engine. And the two categories, they have the same number of variables, MPG, DISP. All we just want to do, how are we going to construct a simultaneous confidence interval of the difference between MPG in the two groups, between DISP in the two groups, between HP in the two groups, and between WT in the two groups? And that's exactly what we're trying to do here. Okay, but don't forget, when it comes to simultaneous confidence interval, based on what we did yesterday, we have four of them. Okay, now you see the TCI now. Now you're actually going to have four different ones depending on the numbers of variables, because I got four variables. Okay, don't forget, I got four variables. This is the mean for each variable. Okay, and what you see here, I'm trying to figure out the confidence interval for each variable. Oh my God. The something that is being displayed here. Take a look at this. This is one. This very one is trying to say, oh, I'm talking about MPG. 000 mean here, this result is only for MPG, not for DISP, not for HP, not for WT. The second one, oh, one is the second one. This result is actually for DISP, not for MPG, not for the other one. That's why you see 00. So take it. Who doesn't understand this? Is that one? Doesn't understand that? Everybody good, right? Okay. I'm going to move to the next one. Now, what I just showed you there is the Ottolenghi squared, okay, for two groups, confidence interval. Now, what did we just do? Do you know assumption here is that the two groups have the same population covariance. The two groups are the same population covariance, and that was why we pooled. Can you see that? That was why we pooled. But what of in a situation where the population variance is like in classical statistics, where you want to compare two groups? Okay, we could have a situation where the two population variances are not the same. Now we also want to do the same in multivariate setting, where the population covariance is not the same for the two groups. That's what we want to do now. Take a look at that. Statistics is about obeying assumptions. What make our models to be fantastic is when we strictly follow assumptions. We got some method that we use when assumption holds. We got some method that we use when assumptions are violated. Right now, we want to consider a heterogeneous covariance situation where I actually want to compare two groups, but the covariances are not the same. Oh my God, take a look at this. Look at what I'm writing now. Can you see that there's a K attached to this covariance? It's trying to tell you the covariance structure for the first group and the covariance structure for the second group not expected to be the same. Now, we cannot use the conventional t-square for that. We need to be able to adjust, okay? When it is not the same, we need to be able to adjust. Okay, oh my God, the t-square is going to change. Take a look at this now. You are never going to see a pool covariance anymore. We only put covariances when it is assumed that the population covariances are the same. But right now, they are not the same. So each group is going to maintain its covariance structure. Can you see the t-square right now? That is the t-squared. Okay, in case I actually, and that was why I call that t-square statistic with non-pooled covariance matrices. We don't pool covariance matrices if there's an assumption that they are not the same. We only pool them if there's an assumption that they are the same. Is there any question? Okay, now, you see that? Now, the probability, if I want to construct the confidence interval, then the probability of the t-square less or equal to the chi-squared is much more the confidence, 1 minus alpha. And I'm only going to use the chi-squared, don't forget, for large sample approximation. I think I said that the other time, okay? So the t-square will follow a chi-squared, for situation where the sample size is sufficiently large, okay? And that's why we said it's going to be asymptotically work for non-normal motivated data too. So imagine you want to compare two groups and there's a violation of normality assumption. So if sample size is large enough, there's no problem. According to central limit theorem, when you are choosing from a population that is not normal, okay, provided you choose a sufficiently large sample size, then we expect the statistic to converge, the distribution for statistic to convert to normality. Okay, so the situation where P is small, when I say P small, the numbers of features, numbers of variable. Okay, we assume no, and we assume normality. So so we're going to take the minimum of n1 and n2 minus p. So then we're going to have a t-square defined as this. So what am I trying to talk about? Different formula. T-square followed chi-squared for sufficiently large sample, but situation where the minimum between n1, what I say minimum, n1 and 2. Sample size for group 1, sample size for group 2. I find the minimum, I subtract p from that. And if that is small, then I'm actually going to assume that. Okay, please pay attention. There's a huge work here. Now take a look at this. Okay, if you take a look at this, V here, the V here, you need this formula to compute the V. Don't forget your P is a number of features. Your SK, when I say SK, okay, it means I need the covariance for X1, the covariance for group 1, the covariance for group 2, S1, S2 in this case. That's why you see I'm going to sum that, case start from 1 to 2. Then if you get X1, the covariance for group 1, and the covariance for group 2, then you'll be able to get X0. There's S0 in the formula. This is S0. The X0 in the formula. This is how you're going to get it. So please pay attention. Now, what are we trying to do? For situation, don't forget, why do we find ourselves here? Okay, if the sample size is large, t-square is going to be that. Oh, sorry. If the sample size, if this one is small, what do I mean? If this guy is small, if the minimum between the sample size from group 1 and the sample size from group 2, okay, the minimum of that minus p is small, and we assume normality, that is when we can make use of this formula for t-squared. and we assume normality. There are two conditions. Okay, the minimum of n1 comma n2. Okay, it's just like um what you have done before. Okay, so I can write it here. Where you're going to write n minus p. Okay, but here our n is going to be the minimum. Okay, between the sample taken from group 1 and the sample taken from group 2 minus p. If that is small and we assume normality, we're actually going to make use of that formula. And v in that formula, that this is that this is how it is computed. Okay, so pay attention to that. You don't understand, ask me question. I'm actually going to move. This is now. Okay, how do we do it? How do we do it in R? This is how we do it in R. Okay, this is how we do it in R. Now, if I want to go back to that example. Okay, now let me tell you this. I want to compare two groups. I want to compare cars with 4-cylinder engine with car with 6-cylinder engines. I want to consider them over the same numbers of variables, 4 variables. Before I can compare parametrically, we actually need to investigate assumptions. Assumptions is that the two group, we need to look into covariance structure of group 1, the covariance structure of group 2. We have a test, multivariate normality test of equality of covariances. If they are the same, we use the one with the pool. If they are not the same, we can't use the one with the pool. We use the one with the non-pool. And you know what we're assuming here now? We're actually assuming that the covariance structure are not the same. Okay? So that's exactly. Now, when I started, when I started, okay, if you take a look at how do I know? Oh my God. If you take a look at this one and this one, there are two different tests here. Please pay attention. This one is different from this one. The first one, we are zooming equal covariance matrix. Can you see? VAR equal variance, that it means variance equal true. Okay? Now, the p-value, when we are zooming equal covariance matrix, is this guy here. When you are zooming where there's heterogeneity in the covariance matrix, the p-value is this guy here. So the two will not give you the same p-value. Now the question now is, how do we know the p-value we're going to use? Then to be able to know the p-value we're going to use, number one, it depends on the assumptions that we are citing. Number two, maybe we have investigated assumptions. We have a way to test. We have the way to test. I remember in lower level statistics where you want to test for, where you want to compare two groups focusing on one variable, we have what we call, there's a test for equality of variances that we call Levini test, Bartlett test, and so on like that. Okay, now I want to move. Pay attention. Okay, do you understand? Ask me a question. Okay, now, oh my God. I'm done with two groups. Now in this class, I've walked you through one group. Now we've done two groups. Okay, it's like comparing performance of students in various subjects in two schools. Can we have a way to go beyond two schools? If you want to go beyond two schools and you only want to compare the performance of students in one subject, of course, we're going to use one-way analysis of variance. But situation where we actually want to go beyond one subject, then we're going to consider multivariate analysis of variance. And just like what we've been doing, can we have a way to have a recap on one-way analysis of variance for one variable? Of course, in the moment you understand that, all what we're just going to do is to have an extension of that. Now let's get started. Ronald Fisher, 1925, put forward analysis of variance tests if you want to compare means in more than two groups. Okay, we use F-tests called analysis of variance tests, and that come with assumptions. Okay, assumptions of normality. Okay, the groups have to be independent, and the group must have equal variances that we call homoscedasticity. There must not be outlier. I remember my PhD work that I've defended in 2016 in a university in Nigeria. I actually work on how do we, when there's a violation of assumption, when you're conducting one-way analysis of variance, how do we reparameterize the F test? How do you reparameterize ANOVA test, to make it robust? So that project was initiated, from University of Ibadan, Nigeria, and I think I had the opportunity of presenting that same work at the University of Oxford in the United Kingdom in 2015. So that was what I work on. But right now, so let's take a look at that. What I'm just trying to tell you is that we're actually going to have a module. That is one-way analysis of variance module, where X is going to be the response, the mu is actually the overall mean, and alpha, that will be treatment effect. And of course, you're going to have error, and the error is assumed to follow normal distribution. Now, you know how we do it in a one way. Of course, one way means I have one factor, one categorical factor. And of course, we're actually going to have an estimate of the mean, the estimate of the treatment effect, as you can see right now, and the estimate of the error time. And we know we normally, based on that, when you are using, the idea behind the analysis of variance means the splitting or the breaking down of the total sources of variation into two components. Okay? Now, if I actually want to test the quality of means, I'm actually testing that the treatment effect equal to 0. Now, if as a guess, it is not equal to 0, okay, and here I have G numbers of groups, and of course, it means I should be ready. This guy here is the total variations, okay, this guy here, the total variation. That's what we call the sum of square total. The total variation can be broken down into explained and unexplained. Explained variation is sum of square between. Okay, let me tell you this. Your model, even though we want to use the model to depict reality, a model cannot give us an exact characterization of reality. We're always going to have unexplained. Unexplained is sum of square within. Explain is sum of square between. So the analysis of variance will enable us to decompose the total sources of variation into two components. Okay, so that is exactly trying to explain the idea that we're using. Okay, now let's take a look at this. Now, we're going to have, what is the test statistic? The test statistic is actually F test. Okay, in my work, I expanded that F test. I call it, to become exponentiated F test. Okay, so this is an F test. And when you take a look at that F test in the formula, the SSB is the sum of square between, which is the explained variation. Okay, the sum of square between. Okay, the SSB here is this guy here. Then SSW is the sum of square within the unexplained variation. Then G minus 1, the G minus 1 means the degree of freedom for group. And N minus G will be the degree of freedom for error. Okay, so take a look at that. And you know what? How do we compare? If I compare this guy with this guy, I'm going to check this guy from a table. Okay, we have a table of F with degree of freedom, G minus 1 and M minus G, okay, with a level of significance. So if I get my F, if I compare the F statistic with that F critical, if that is greater, then I'm actually going to reject the non-hypothesis. Or I can even have a table Okay, I can have a table. Okay. Let me show you the table. Okay, I can have a table. I can have another table, for that. But you know what? Away from this now, and I want to have a multivariate extension of one-way analysis of variance. The one-way analysis of variance is trying to say, why is it called one way? Oh, one factor, one group, one factor, one factor, one categorical factor. Okay, that's what I mean. We could have two-way as well. Okay, so now if I now take a look at this, what assumptions am I having here? Oh my God, equal covariance matrix across group. Take a look at that. Okay, okay, the G is the numbers of groups. Now the module is going to change to this. Of course, in the module now, they are going to be matrix. Okay, they are each of them going to be matrix. Okay, so we are writing that in that form. Now, let me tell you this. Uh, and this is how you can find the estimate of the mean, the estimate of the treatment effect, the estimate of the error, your X bar. This is going to be, this guy is the overall mean. If I want to get the overall mean, okay, the overall mean, and this one is the mean per group. There's going to be the mean per group. Get what I mean? Okay, now I'm going to move right now. So pay attention. Now, the other time, we have a way to decompose the sum of square total into sum of square between and the sum of square error for univariate case. We're also going to have the same in multivariate case. Take a look at that. Instead of us to write x minus x bar all squared, we are writing that in matrix form. And we're going to call that sum of squared and cross product decomposition. So take a look at that. So this is the total variation. This is explained, and this is unexplained. And you know what? Because I want to write that in short form, if I let W to be this one, and I let this one to be B, please pay attention. This is going to give you matrix. This is going to give you matrix. This is also going to give you matrix. So if I let W to represent this guy, okay, look at that. W representing this guy, okay. Now, mathematically speaking, this guy is also the same as this. If you don't want to waste your time, would you know what you just need? The second one, I just need to find the covariance structure for each group. Sum them. Before summing them, okay, the sample size in each group minus 1 multiplied by its covariance structure, we add them up. So that guy, so what I'm trying to say, instead of using this one, this is fantastic. That's W. Now, if that is W, of course, you know how to get the SK, right? How to get the covariance structure. We've done that in this class. Okay, you see that? The sample covariance structure divided by n minus 1. Don't forget that. Now, how do we set up the table? Please pay attention. We have one-way ANOVA table. We also have one-way MANOVA table. So in the source of variation, I'm actually going to have between. So this is going to be called sum of square cross product matrix. You can see this is the B, the W. Then the total is just going to be B plus W. Oh my God. Do you remember where we're doing addition of matrices, subtraction of matrices when we earlier in the semester? So if I know B and I know W, the total variation is just B plus W. Okay? And look at the degree of freedom for between G minus 1. The degree of freedom for within, you can see that, and you can see the degree of freedom for total. Okay? Now, how am I going to get the test statistic after setting up this table? Please pay attention. Okay. Oh my God. Let me first. What hypothesis am I testing? I'm testing this. Why do we have 0p? Okay. Vectors of zeros. Don't forget, depending on the number of what? Numbers of variables. P is the numbers of variables. Okay, so the treatment, if the treatment effect equal to 0, you know what I mean? If the treatment effect equal to 0, it means there is no significant difference between what you are comparing among the G numbers of groups. But what is going to be the non-hypothesis? What is be the alternative? Can you see that now? Then what will be the test statistic? The test statistic is going to be this. Oh my God. If you take a look at that W, determinant of W, that is more or less like a generalized variance. You remember the other time we did two variance. So determinant of the within and the determinant of the total, that is what that ratio is called wiki lambda. Wiki lambda is a test statistic that we use in the analysis of variance. Now, when you get wiki lambda, how do we reject H naught if the wiki lambda is very small than the expected under the non-hypothesis. Now, but let me tell you this. We could have different critical value and test statistic depending on the numbers of features. For instance, if P equal to 1, I'm only considering one variable, and I'm comparing two or more groups. This is going to be my test statistic. Now, in this test statistics, you see wiki lambda. You see that wiki lambda star. That wiki lambda star, you need to force estimate that here. Can you see that? You get a wiki lambda star. So depending on assignment, so this is now going to serve as your test statistic. This one, then you compare with this guy, the critical score. If this guy is greater than that, you reject H naught. What if P equal to 2? If P equal to 2, you have two variables and two or more groups, then your test statistic become that, and this is what you're going to check. You see, you are checking from F table in all of that, except that you are checking a different degree of freedom. And of course, you can see the formula. Okay. So if I give you assignment on this, then you need to be able to, for you to be able to know the appropriate test statistic to use, that depends on the numbers of variables and the numbers of groups. Okay. And let me tell you this. All of these, they are for small sample. Okay. Our situation where n is large and H naught is true, then instead of you to be checking from F distribution, you're going to be checking from chi-squared. Okay. But your test statistic is going to change. Your test statistic is going to be this. Don't forget, your lambda, your wiki lambda is still what you get from the other time. So you do the log of that, then n minus 1 minus p plus g, there follow chi-squared. So you compare this with chi-squared for you to be able to know whether to reject the null hypothesis or not. Okay. Now, apart from wiki lambda, we also have other popular multivariate analysis of variant, the one by Lolly Otelin trace, the pillar trace, and the Roy largest roots. But I'm actually going to say all of them is actually based on B and W, the between and the within. Okay. And here I said some evidence. We have some evidence that pillar tree is more robust to non-normality. So in case where there's a violations of normality assumption, you may not be able to use the conventional wiki lambda. So we have evidence that pillar trace is actually more robust in that situation. Now I provided an arrow code. Okay, of course, for the same thing that but except that we're actually going to have more than two groups. Maybe I want to compare engine with 6-cylinder, with 8-cylinder, with 10-cylinder, more than two groups. Okay, so what and you know what? I gave different kind of test statistic here. The one this is for pillar. Okay, the one for weak. Okay, and the one for Roy. Okay, you can compare the p values. Okay, so I would advise that you check through all of that. Okay, now the next is the variance of treatment effect difference. Let me see this, whether I can use one. Okay, you know what? Oh, that's a lot. I'm going to take it easy. I'm going to start from here, from the variance, because what we have left, we have, uh, wait a minute, we have, I'm going to start from tomorrow. I'm going to start from here. Variance of treatment, effect difference. Then from there, we're going to go into simultaneous confidence interval for that. And not only that, I'm going to show you some R code. Then I'm also going to talk about how do we test for equality of covariances, because what validates the use of multivariate analysis of variance is that the covariances has to be the same. How are we going to know that? We have a test. I'm going to walk you through that tomorrow. Then I'm going to give you how to do that in R. And after that, I'm actually going to go into two-way ANOVA. The two-way ANOVA is when I have two categorical factor. The other time in cars, I'm only considering, I'm actually classifying them based on the numbers of engine cylinder. But what if I also want to put into consideration another categorical factor? Then we're gonna have a two-way ANOVA. So just like the way I started, I'm gonna start from two-way ANOVA univariate. Then I'll finally go to the multivariate version as well. So presented to you, this is what we're gonna have tomorrow. And all of them come with the arrow code. So if I were you, when you study the formula, also study the arrow code. Okay, so tomorrow we're going to continue from um the this is where we're going to start from tomorrow. Variance of treatment effect difference. Is there any question? Is there any question before I go today? Any question? Okay, so tomorrow will be our last day of meeting in the week. Of course, there's going to be public holiday on Friday, which is July 4. Okay, so we meet it tomorrow. Bye for now, everyone.